Welcome to this video on the passive circuit elements in the frequency domain. This is part of a series of videos on circuit analysis in the frequency domain. We want to find out the relationship between the phasor current and the phasor voltage at the terminals of the passive devices. Starting with the resistor, suppose we have a resistor with resistance value of R, and assume that a sinusoidal current with amplitude Im and phase theta I flows into a resistor. The voltage across the resistor is obtained by multiplying the current by R. If the current is represented in phasor form, then multiplying it by R gives the voltage in phasor form. And we find the VI relationship for a resistor. We can see that V and I are in phase. This means that they both reach their maximum and minimum values at the same time. You can see a numerical example along with waveforms obtained through simulation. The red plot represents voltage, whereas the green plot represents current. Now let's find the VI relationship for an inductor. Assume that a sinusoidal current with amplitude Im and phase theta I flows into an inductor. The voltage across the inductor can be determined by multiplying the inductance value by the time derivative of the current. By representing this result in the phasor form, the VI relationship for an inductor is obtained in the phasor domain. As we can see, the voltage and current are out of phase by 90 degrees. In fact, the voltage leads current by 90 degrees. Alternatively, we can say that the current lags the voltage by 90 degrees. You can see a numerical example along with waveforms obtained through simulation. The red plot represents voltage, whereas the green plot represents current. Now let's find the VI relationship for a capacitor. Assume that a sinusoidal voltage with amplitude Vm and phase theta V is applied to a capacitor. The current flowing into the capacitor can be determined by multiplying the value of capacitance by the time derivative of voltage across the capacitor. By representing this result in the phasor form, the VI relationship for a capacitor is obtained in the phasor domain. As we can see, the voltage and current are out of phase by 90 degrees. In fact, the current leads voltage by 90 degrees. Alternatively, we can say that the voltage lags the current by 90 degrees. You can see a numerical example along with waveforms obtained through simulation. The red plot represents voltage, whereas the green plot represents current. An important concept in circuit analysis in the frequency domain is impedance, which is defined as the ratio of a circuit element's voltage phasor to current phasor. Impedance is measured in ohms. Note that impedance is not a phasor because it is not the coefficient of e to the j omega t. The imaginary part of impedance is called reactance and is denoted by uppercase X. The impedance and reactance of the passive circuit elements are listed in this table. Because the impedance is the ratio of voltage phasor to current phasor, we can use it to obtain voltage or current phasor when either of them is available in phasor form. We can do this for the numerical examples that we had earlier. The case of the resistor is very straightforward because R is real and does not cause any phase shift between voltage and current. In fact, when dealing with purely resistive cases, the time domain solution is already very straightforward. The convenience of using the impedance can be seen when dealing with inductive or capacitive cases. As you can see, For the case of inductor, the same result can be achieved just by complex number algebra, whereas in the time domain you will need to take the derivative with respect to time and multiply by L. Similarly, for the case of capacitor, the same result can be achieved using complex number algebra. Two examples are provided. As you will see in the solutions, you can easily find the time domain result by applying the inverse phasor transform to the phasor representation of the result. However, you are encouraged to solve them in time domain as well.